Greetings, I'm Scott with Blossom Consulting and Engineering, and first off, I'd like to say thank you to the ASFPM for the opportunity to present today. It's been an amazing experience over the last 15 or 20 years, and we've had the chance to present all the way from Atlanta, Georgia to Seattle, Washington, and I can't wait to see everybody upcoming in Florida. I'd also like to give a shout out to our local chapter, the Virginia Floodplain Management Association, specifically for allowing us the opportunity to use the WARDS floodplain model at an upcoming K-12 event. We can't wait for the opportunity to get back out into the community and talk to the younger generation about the importance of floodplain management. And I'd also like to say thank you to our team at BCE. They play not only a critical role in the projects that we have the opportunity to present today, but also into the presentation itself. Blossom Consulting and Engineering is headquartered in Williamsburg, Virginia, and we are a group of agricultural, biological, civil, and environmental engineers with specialty and focus in water resource engineering. You can see our 5 main service areas here, which range from floodplain management to watershed analysis and modeling, urban stream restoration, dam safety, and stormwater management design. Today we're going to talk about interdisciplinary forward-thinking approaches to floodplain restoration and tidal wetland restoration. The interdisciplinary piece is something that we're all very familiar with from our involvement in the natural and beneficial functions of the floodplain. The forward-thinking piece is the utilization of hydrologic and hydraulic modeling in somewhat of a predictive way and methodology to evaluate a variety of storm-driven scenarios and the effect that they have on the hydraulic capacity as well as the ecosystem components of these systems. The structure of today's presentation is something similar to what we've used in the past. It's essentially an exploration of a few different case studies in different topographic and climatic conditions and an evaluation of the H&H modeling routines that were selected and how each one of those was utilized to inform the designs. In this particular case, we're going to evaluate 5 different case studies in very different settings. And the first one that we're going to look at is a tidal wetland mitigation bank. This particular property is about 300 acres, 150 acres of which will be placed into a mitigation bank. The goal of the project is to re-engage tidal tributaries which have previously been cut off by berms or small low-head dams. This multifaceted project involves not only the creation of low and high marsh zones and the tidal tributary restoration, but also non-tidal mitigation necessary to mitigate for the impacts necessary to construct the tidal wetland restoration. There's also opportunities for oyster habitat restoration and stream restoration of the transition zone between the tidal and non-tidal areas. And that's going to be a reoccurring theme throughout this presentation. We're going to evaluate the hydraulic modeling in that intertidal zone. For this particular project and hydrologic modeling, we're using HEC-HMS and starting with the USGS 1 meter DEM, which is then converted to a mean low water datum using a local NOAA tide gauge. This is absolutely critical because we're evaluating the effect of the tidal fluctuations and that seasonal pulse on the vegetation that's existing and that we're going to propose. For this project, in terms of the hydrology, as I noted, we use HEC-HMS version 4.9, and we're using a simple canopy SCS curve number methodology with SCS unit hydrographs that are later imported into RAS, and we're going to talk about that. We utilize the automated watershed delineation tool to help define our basins and subbasins, and we're also defining the sinks and break lines that really allow us to accurately model the system. We're defining the sinks and the focal points and the nodes where we want to analyze pre and post restoration conditions. As I noted, the hydrographs are later imported into RAS, and we're using HEC-RAS version 6.1 in order to evaluate this tidal system, and the boundary conditions on the downstream end are essentially the NOAA tide gauge. We're using the break line system to further define and flex the 2D mesh and the surface that we've created from the DEM. By using these break lines, we're really able to focus in and drill down into the tidal tributary channels that we're looking to restore and evaluate the hydraulic characteristics in 2 dimensions. Okay, so this is what the results of the existing conditions analysis look like under a king tide. And the king tide is essentially the highest tide that we have seasonally here in Virginia. You can clearly see the areas where the tidal tributary flow is impeded by existing berms, even in this king tide event. So as I noted, our goal was to re-engage those tidal tributary channels, not only during the king tide, but during a regular tidal event, and put the system at an appropriate elevation to where the vegetation that is installed is able to sustain those conditions. Okay, so in terms of designing the proposed geometry of the tributary channels, we're utilizing some of the concepts in natural channel design methodology, where we're evaluating reference reaches not only on a scale that's very defined and resolute, but also using aerial imagery. In this particular case, you can see one of the tidal systems that we're evaluating at a very low tide in the fall. And in this situation, we're able to look at the geometry and sinuosity and use those reference ratios and dimensions to design the pilot channel of the system we're looking to create. This picture I actually just took today, and you can see the difference that the vegetation makes, not only in terms of the look, but also the function of the system in holding together the floodplain valley. Okay, so this is showing after cutting, using that natural channel design methodology to arrive at our proposed geometric conditions, not only for the pilot channel, but for the low and high marsh zones that we're looking to create. And then cutting essentially in a layered fashion that into the existing condition surface to create our proposed surface, and then running those same tidal conditions over that proposed surface and evaluating the effects. In this particular case, since it's a mitigation bank, it's absolutely critical to hit the success criteria, which is the seasonal inundation of the vegetation zones that we're creating. So really the credit is defined in terms of the functional ecosystem lift that we're able to attain above the existing conditions. This is how the modeling currently looks. As I noted, we're in the conceptual phase of this particular project. And what's interesting to note is not only are we able to re-engage the tidal flow up into those tributary channels by removing the berms and any impediments to flow, but we're also evaluating the potential to create non-tidal mitigation at the heads of these systems. So we've now brought in the hydrographs that we generated from HEC-HMS and are fluctuating the downstream boundary conditions along with those precipitation-driven events and evaluating each one of these tidal tributary channels. We're looking to use some of the sediment transport capabilities in HEC-RAS to make sure that we get the appropriate profile slope to allow the system to flush. And also, as I noted before, considering sea level rise and how that is going to affect the success of this particular system. So for this analysis, we selected the 2017 NOAA Intermediate to High Curve, which projects about 3 to 4 feet of sea level rise at this particular location in the year 2070, so pretty significant. And as we noted before, hitting the vegetation zones essentially within a 3-inch accuracy is absolutely critical to the establishment of the tidal vegetation. In this case, the areas where the tidal wetlands would be expected to migrate are essentially within the buffer zones that are required for the tidal wetland mitigation. So what we're doing is flattening our slopes and increasing our buffers to allow room for the tidal wetlands to migrate. And so those areas will be placed within the conservation easement within the overall mitigation bank as well. All right, switching gears fairly significantly in terms of geography and climatic condition, let's look at a project that's located at a 100-year-old military facility in a riverine setting. This particular project is called Beaver Creek, and the goal was to create a watershed model to simulate a whole range of storm-driven events, to identify road overtopping and potential to integrate solutions to reduce road overtopping and increase our ability to deploy during extreme storm events. For this particular project, we combined the hydrologic and the hydraulic modeling into a PC swim model. And what we're showing here is the subdivision of the approximate 4,000 acre watershed into 5 subbasins. We also organized the model according to 14 grids that structured the existing SDS FIE compliant GIS database that essentially inventoried and cataloged all of the storm drainage structures that influence how the system performs. As a component of the analysis, we were able to get out into the field and survey with our team, which was McKinnon Creed and Sims, and evaluate roughly 2,500 structures and 600 hydraulic cross sections in the natural channels that connected the storm drain infrastructure. So a very complex model that you can see is kind of graphically represented here, with the blue channels being the natural channels and the yellow and green being the storm drainage infrastructure. As I had noted, the goal of the project was to identify which roads overtopped when, and the Corps defined the storms or the storm design scenarios that we were to evaluate. In this particular case, we were looking at 10 and 50 year standard 24-hour design storms, but also compounding a second storm which occurs 7 days later of a similar frequency or a similar duration and magnitude. In addition, we simulated 200-year, 24-hour, standard routines and loaded in a 40-year precipitation data set that allowed us to bracket certain times in history and evaluate how the system was responding to, again, recurring storm events or significant storm events. As I noted, the goal of the project was to find solutions to improve our ability to deploy during extreme storm events. And so once subbasins were identified as potentially being problematic, we're able to go into those subbasins and create more defined models and evaluate potential solutions in 2D. So some of those solutions, such as off-channel wetland storage or additional retention or detention within the watershed, or floodplain culverts, we're able to evaluate in more detail in 2 dimensions and consider integration of some of the other tools that are now available to us in the water resources realm in terms of installing gauges and monitoring stations within the system to allow us to get real-time alerts that are then communicated to those that need that information in terms of responding and deploying again during these extreme storm events. All right, this project, shifting gears again, is located in the Shenandoah Valley. It's called Cold Springs, and it's about a mile of stream restoration. And it's interesting to discuss because at the military base project, we essentially got to the point to where we were conceptualizing design solutions and modeling those and presenting some solutions such as, stream restoration within the vicinity of road crossings coupled with floodplain culverts or off-channel storage. In this particular project, we had the opportunity to implement the natural channel design and stream restoration and evaluate the effect of that stream restoration on an upstream road crossing. This project was actually implemented for the purposes of creating a nutrient bank and helping to meet Chesapeake Bay TMDL goals, which are essentially quantified by phosphorus, nitrogen, and sediment. So we're looking to reduce bank erosion associated with a previously impacted agricultural channel and quantify the nutrient reduction associated with that. It's interesting to note that in Virginia, we not are only looking at reduction in sediment and phosphorus and nitrogen through reducing bank erosion, but also looking at the effect of additional floodplain storage and creating sinks for nutrients as well, nutrients and sediment as well. For this particular project, we're using one-dimensional HEC-RAS. It's located in a FEMA floodplain, and it's really a project that involved the balancing of stakeholder and adjacent landholder or adjacent land user interests, that balance of agricultural land uses with adjacent infrastructure, all within the same floodplain valley. As you can see, we bisected the floodplain valley, and our goal was to evaluate not only the stream restoration in the smaller bankful channel, but also how does the grading of the terraces affect the no rise and no adverse impact analysis. Here we're looking at a as-built survey. So the red channel is laid upon the proposed conditions. This project was constructed a few years back. And it's interesting now to look back at the design conditions and consider what happened during construction. So this particular project was located downstream of Lofton Lake, which was recently upgraded to pass the PMF. And the project went to construction in the fall. When we were doing the analysis, it was in the spring and it was in the summer, and we actually had some opportunities to see it in the fall as well, but the spring and summer flow was highly controlled, and essentially the channel was reduced down to a very small thread, which essentially kind of meandered through the existing agricultural field. We had to consider not only a very small, almost drought condition flow, bankful flows, 100-year flows, and also the flows that were discharged from the upstream dam. As I noted, this project went to construction in fall, and we actually experienced 7 bankful events during the 6-month construction period, which is really unheard of and challenging to deal with in terms of gathering the as-built survey data. So in terms of lessons learned, the seasonal variability of flows as controlled by upstream dams should be considered a little bit more intricately in terms of the season in which the project goes to construction. This is a photo from actually during construction directly downstream of the roadway which I had referenced earlier. And as I had noted, through the grading and the terracing of the stream restoration, we were able to actually improve the storage downstream of the road crossing and lower the water surface elevations by allowing that runoff a place to disperse and access the floodplain. In terms of the stream restoration goals, we were actually trying to engage the floodplain or the internal floodplain benches as frequently as possible to saturate the adjacent wetland benches to that small pilot channel. Here's another view that's starting to show a little bit more of the extents of the valley. And as I had noted before, this is a real balance of stakeholder and adjacent landowner interest because there's a railway that actually paralleled the entire floodplain valley. And we were also looking at balancing the agricultural landowners' interests. So in terms of defining the riparian corridor where the more frequent events are going to access, and also evaluating the agricultural terraces that are adjacent to the project and analyzing how frequently those terraces would be accessed. So really a balance of land uses and goals within the overall valley. Okay, so shifting gears again, this is a little bit different type of project that we were involved in from a post-hurricane recovery effort. This project is located in the British Virgin Islands, and this particular site was directly impacted by Hurricanes Irma and Maria, which were two Category 5 hurricanes that essentially passed directly over this island chain. They sustained significant damage, as you can imagine, and we were faced with the real condition of island browning, which is shown here by this aerial imagery, where essentially the islands were stripped of their vegetation, leaving a surface that was very exposed to continued erosion. For this particular project, the community was very resilient and started their recovery efforts essentially with restoring basic services. So rainwater harvesting is a requirement in the islands and was literally one of the first elements that was repaired post-hurricane. We were able to help with the site approximately 1 year after the event, and we're considering the best practices to restore the site topography and integrate depressional storage for more frequent events into the restored site plan, and also identify areas where terracing and elevation could be considered in the rebuilding efforts. This is a comprehensive, long-term project where it begins with some of the basic services that we've discussed, but also ends with restoring some of those first lines of defense in terms of enhancing and restoring the coral reefs, which is the next step in this particular project. In terms of the modeling strategy, obviously the events which occurred here are of a magnitude and scale which were very difficult to handle in terms of design. And you can see here a representation of the observed water surface elevation as communicated to me from some of the folks that were there during the event. We were able to assist the community to consider not only the surge and the extreme energy coming from the coastline, but also the contributing watersheds which are coming off the hillside, as you can see here, where that later needs a place to exit as the surge recedes. You can see some of the rebuilding efforts represented here, and this community is currently going through rebuilding and essentially regaining their momentum for sustaining their lives here on the island. As we wrap up, I'd like to explore a little bit of a comparison of the flows that are associated with dam breach inundation modeling and floodplain analysis. And as we get into that discussion, this is a project that we had the opportunity to participate in as a specialized floodplain analysis component, where we were working hand in hand with RES doing the stream restoration design and evaluating the pre and post project conditions in terms of no rise and no adverse impact. What's interesting to note about this project is there's an upstream high hazard dam that also has a flow range that is of a different magnitude than even the 100-year event. So for this project, we had the opportunity to create a model which extended not only through the riparian corridor, but also up into this golf course, which serves as additional storage during extreme storm events. So for this project, again, we considered not only the seasonal low flows and the bankful flows, which control the channel geometry, but also had to consider the 100-year flow for no rise and no adverse impact analysis, and be aware of the discharges that are associated with the breach hydrographs. In Virginia, we have a kind of renewed focus on significant and high hazard dams. And recently, BCE has been involved in the evaluation of a variety of dams in terms of hazard classification and breach modeling. And utilizing some of the techniques that we've discussed today, we're able to pretty quickly get into a compiled and structured model that allows us the opportunity to look at a variety of different events, as we've been discussing. And in this case, we're using HEC-HMS to evaluate unsteady breach hydrographs, which are then imported in HEC-RAS for the inundation modeling. The whole purpose of this analysis is to define the hazard classification and the spillway design requirements in terms of dam safety, and also identify downstream hazards and risks and evaluate them in terms of what would need to be improved to reduce risk and downstream hazard. Putting all this together, we wanted to talk briefly about a project that involves the interface between that tidal and non-tidal zone, as we were talking about before. And the different types of modeling that are available to us now allow us the opportunity to further evaluate that interface and also consider both floodplain flows and breach flows in this intertidal zone. This will allow us to improve our confidence for risk planning and improve for better emergency planning as well. This particular project was an emergency water line repair. And it's interesting because the water line was actually located essentially at that zone between tidal and non-tidal influence. For this project, we utilized the effective HEC-RAS one-dimensional model, and were able to pretty quickly arrive at a no-rise condition by nesting the aerial water main crossing behind the vertical profile of the road. However, it's also interesting to note that we are currently evaluating this very system in terms of breach inundation modeling. And as we've discussed, there's a huge opportunity to improve the way that we are evaluating infrastructure improvements and road overtopping, utilizing fluctuating boundary conditions to analyze a range of design storms. And then there also is opportunities to evaluate two-dimensional modeling as we get into some of the potential improvements that involve off-channel storage and detention. At any rate, we're looking forward to present this project at a future conference because it'll be a very interesting comparison of floodplain mapping and breach mapping with consideration of infrastructure and improving risk management and hazard identification. With that, I'd like to say thank you for your time again, and thank you for the opportunity to present today. And please contact us if you'd like to discuss or have any further questions, and I'll be hanging around for a few minutes for questions as well. Thank you.